Humanity stands at the precipice of a fundamental thermodynamic bottleneck, a crisis of energy that dictates the survival or extinction of our species. To transcend our current limitations and ascend to the status of a Type 2 civilization on the Kardashev scale, we must harness the total energy output of our host star. The sun radiates an incomprehensible 386 yottawatts of power continuously into the void of space. Earth, a minuscule sphere located 150 million kilometers or 93 million miles away, intercepts less than 1/1000th of this stellar output. This infinitesimal fraction has driven every meteorological event, every biological process, and every technological advancement in the history of our world. However, to fuel the exponential growth of human industry, interstellar propulsion systems, and planetary engineering, this passive energy collection is fundamentally insufficient. We must construct a megastructure of unprecedented scale, a Dyson swarm, consisting of quadrillions of independent solar collectors orbiting the sun. To achieve this monumental feat of astroengineering, we cannot rely on the resources of Earth. Nor can we mine the asteroid belt, as the mass required is simply too vast. We must commit the ultimate act of planetary engineering. We must completely dismantle the planet Mercury. This is not a speculative fantasy, but a mathematically rigorous necessity dictated by the laws of orbital mechanics, material science, and exponential manufacturing. The destruction of Mercury is the only viable pathway to secure the future of humanity, transforming its lifeless mass into a swarm of mirrors covering 30 quadrillion square kilometers or 11 quadrillion square miles of space. The selection of Mercury as the sacrificial body for this stellar megastructure is dictated by a confluence of optimal physical and orbital characteristics. Mercury orbits at an average distance of 58 million kilometers, or 36 million miles from the Sun, placing it deep within the stellar gravity well. This proximity provides an overwhelming advantage in solar irradiance, which is nearly 7 times greater than the solar energy received at Earth. This intense radiation is the primary power source required to initiate and sustain the exponential mining and manufacturing processes. Furthermore, Mercury possesses a uniquely high metallicity, with a massive iron core that constitutes approximately 85% of its planetary radius. This core is surrounded by a relatively thin mantle of silicate minerals, providing the exact elemental precursors required for constructing solar reflectors and structural frameworks. The surface gravity of Mercury is roughly 38% of Earth gravity, which significantly reduces the escape velocity required to launch manufactured components into solar orbit. The escape velocity is only 4.25 kilometers per second, or 2.64 miles per second, a critical metric that minimizes the energy expenditure for our electromagnetic mass drivers. If we were to attempt this construction using Venus or Earth, the gravitational penalty would render the project thermodynamically unviable. Mercury also lacks a substantial atmosphere, possessing only a tenuous exosphere, which means there is zero aerodynamic drag to impede the continuous launch of millions of solar sails per day. The vacuum environment allows for pristine metallurgical processing, free from oxidation or atmospheric contamination, enabling the production of atomically perfect reflective surfaces. To dismantle a terrestrial planet, we must overcome its gravitational binding energy, which is the total amount of energy required to pull all of its mass apart to infinity. For Mercury, this value is approximately 1.8 times 10 to the power of 30 joules. This is an astronomical quantity of energy, equivalent to the total energy output of the Sun over a period of nearly 54 days. It is physically impossible to deliver this energy through conventional explosives or kinetic impacts. Instead, the dismantling process must be a gradual, self-sustaining thermodynamic operation powered entirely by the Sun. We will initiate the process by landing a highly specialized package of automated manufacturing units, often referred to as von Neumann probes, on the sunlit equator of Mercury. These initial machines will utilize concentrated solar power to melt the local regolith, extracting iron, silicon, aluminum, and titanium through high-temperature electrolysis. The first products manufactured by these machines will not be solar collectors, but rather exact replicas of themselves. This initiates an exponential growth curve, where one machine builds 2, 2 build 4, and 4 build 8. Within a surprisingly short time frame, the surface of Mercury will be covered by billions of autonomous mining and manufacturing refineries. The energy required to sustain this exponential replication will be drawn directly from the sun, utilizing massive parabolic mirrors constructed from the very surface they are mining. As the machine population grows, the rate of planetary consumption will accelerate, transitioning from a localized mining operation into a global dismantling process that strips the planet layer by layer. Once the exponential manufacturing base is established, the primary objective shifts from replication to the production and launch of the Dyson swarm components. The factories will begin churning out ultra-thin solar reflectors, constructed from a microscopic layer of polished aluminum deposited onto a durable polyamide substrate. These mirrors will be incredibly lightweight, maximizing their surface area to mass ratio. To transport these reflectors from the surface of Mercury into their designated solar orbits, we will construct a vast network of electromagnetic mass drivers. These linear accelerators will stretch for hundreds of kilometers across the barren landscape, utilizing superconducting magnetic levitation to accelerate the package mirrors to the required escape velocity of 4.25 kilometers per second or 2.64 miles per second. Because Mercury has no atmosphere, these mass drivers can operate at maximum efficiency, firing continuous streams of payloads into space without the thermal stress of atmospheric friction. Upon reaching the vacuum of space, the payloads will autonomously deploy, unfurling their reflective surfaces to catch the solar wind and radiation pressure. They will utilize these forces, along with onboard ion thrusters, powered by the collected solar energy, to navigate to their precise orbital slots. The swarm will not be a rigid sphere, which is dynamically unstable and physically impossible to construct, but rather a complex, multi-layered architecture of independent orbits. This configuration, known as a Dyson swarm, ensures that the individual mirrors do not collide and can dynamically adjust their positions to maintain optimal solar coverage while avoiding the shadowing of other components. The orbital mechanics of a Dyson swarm require meticulous mathematical precision to maintain stability over geological timescales. Each individual solar collector, measuring perhaps 1 square kilometer or 0.38 square miles in area, will act as an independent spacecraft. As they absorb and reflect solar photons, they will experience a continuous outward force known as radiation pressure. At the orbital distance of the swarm, this pressure is significant and must be counteracted by the gravitational pull of the sun. By carefully engineering the mass to surface area ratio of the mirrors, we can achieve a state of perfect equilibrium, where the outward radiation pressure exactly cancels out a portion of the solar gravity. This allows the mirrors to orbit at velocities significantly lower than those dictated by standard Keplerian mechanics, a concept known as a statite or static satellite. This artificial reduction in orbital velocity reduces the kinetic energy required for orbital insertion and allows for a much denser packing of the swarm without the risk of high-speed collisions. The swarm will be organized into a series of interlocking orbital rings, creating a complex geometric pattern that gradually encloses the sun. As more mirrors are added, the total solar energy captured by the swarm will increase exponentially, providing the power necessary to accelerate the dismantling of Mercury. The energy collected by the swarm will be transmitted back to the mining operations on Mercury and eventually to Earth, using highly focused phased array microwave lasers. These transmission beams will be engineered to pass safely through the interplanetary medium, delivering uninterrupted, limitless power to fuel the next stage of human evolution. As the automated mining swarm consumes the silicate mantle of Mercury, the operation will eventually expose the massive, dense iron core. This core represents the most valuable structural material in the inner solar system, essential for constructing the heavier, more complex components of the Dyson swarm, such as the microwave transmission stations and the central processing hubs. The extraction of the core will require a shift in mining methodology. moving from surface strip mining to deep thermal fracturing. The concentrated solar energy from the partially completed swarm will be directed onto the exposed iron, raising its temperature beyond its melting point of 1,538 degrees Celsius or 2,800 degrees Fahrenheit. The molten iron will then be magnetically extracted and processed in zero-gravity orbital foundries, where it can be alloyed with trace elements to create ultra-high-strength structural beams. As the mass of Mercury decreases, its gravitational binding energy will also decrease, making it progressively easier to launch material into space. The planet will begin to physically deform, losing its spherical shape as the equatorial regions are mined away. Eventually, the remaining mass will become so small that it can no longer maintain hydrostatic equilibrium, fracturing into a cloud of debris that will be systematically captured and processed by the swarm. The complete destruction of Mercury will mark a profound milestone in human history, the moment we transition from a planetary species to a stellar civilization. The sky of Earth will be forever changed, as the light of the sun is filtered through the intricate, shimmering lattice of 30 quadrillion square kilometers or 11 quadrillion square miles of solar collectors. The construction of a Dyson swarm is not merely a challenge of mass and orbital mechanics, but a profound exercise in planetary scale thermodynamics. Every industrial process, from the high-temperature electrolysis of silicate regolith to the electromagnetic acceleration of mass drivers, generates waste heat. On a planetary body like Mercury, which lacks an atmosphere or oceans to act as a thermal sink, the dissipation of this waste heat becomes a critical engineering bottleneck. If the automated refineries generate heat faster than it can be radiated into the vacuum of space, the machinery will inevitably melt, halting the exponential replication cycle. To circumvent this thermodynamic limit, the mining infrastructure must be designed with massive, deployable radiator panels, utilizing advanced microfluidic cooling loops filled with liquid sodium or potassium. These radiators must be oriented perpendicular to the sun, facing the absolute zero of deep space to maximize the Stefan-Boltzmann radiation efficiency. Furthermore, the mining operations must be strategically distributed across the surface of Mercury, preventing localized thermal pooling. As the Dyson swarm grows and begins beaming power back to the surface, the thermal load on the planet will increase exponentially. We must carefully balance the energy input from the swarm with the thermal radiation capacity of the mining network. This delicate thermodynamic equilibrium will dictate the maximum speed at which Mercury can be dismantled. It is a mathematical certainty that the process cannot be rushed. It must proceed at a calculated, deliberate pace, governed by the fundamental laws of entropy and heat transfer. The engineering of these thermal management systems will require unprecedented advancements in high-temperature superconductors and metamaterials. The ultimate purpose of the Dyson swarm is not simply to capture solar energy, but to transmit it efficiently and safely to where it is needed. The energy collected by the quadrillions of mirrors must be converted into a transmittable form, specifically highly focused microwave or laser beams. Microwaves are the preferred medium for interplanetary power transmission due to their ability to penetrate planetary atmospheres with minimal attenuation or scattering. Each orbital collector will be equipped with a solid-state phased array transmitter, capable of electronically steering its beam with microradian precision. These individual beams will be synchronized using advanced quantum clocks, combining their power through constructive interference to create a massive, coherent energy conduit. The receiving stations, located in Earth orbit or on the lunar surface, will consist of vast rectifying antennas, or rectennas, spanning hundreds of kilometers. These rectennas will convert the incoming microwave energy back into direct current electricity with an efficiency exceeding 85%. The safety of this transmission network is paramount, as a misaligned beam carrying terawatts of power could cause catastrophic damage to a planetary surface. To ensure absolute safety, the system will utilize a retrodirective targeting mechanism. The receiving station will broadcast a low-power pilot signal, and the orbital transmitters will only fire their main power beams when they are actively locked onto this pilot signal. If the pilot signal is interrupted for even a fraction of a millisecond, the power beams will instantly defocus, dispersing their energy harmlessly into the void of space. This fail-safe architecture guarantees that the limitless power of the sun can be harnessed without endangering the very civilization it is designed to sustain. The dismantling of Mercury and the construction of the Dyson swarm represents a fundamental paradigm shift in the concept of economics and resource allocation. Traditional human economies are based on scarcity, where the value of a commodity is dictated by its limited supply. However, the exponential replication of von Neumann probes introduces a system of absolute abundance. The initial investment required to launch the first seed factory to Mercury is substantial, requiring the combined economic output of multiple nations. But once that seed factory is operational, the marginal cost of producing subsequent factories, mass drivers, and solar collectors drops to absolute zero. The machines mine their own materials, generate their own power, and build their own replacements. This is the power of exponential growth, a mathematical function that starts slowly but rapidly approaches infinity. If the replication time of a mining unit is 1 month, then after 1 year, there will be 4,000 units. After 2 years, there will be 16 million. After 3 years, there will be 68 billion. This explosive industrial capacity will quickly surpass the total manufacturing output of human history. The true challenge is not the physical construction of the swarm, but the software engineering required to manage a network of billions of autonomous, self-replicating machines. The artificial intelligence governing the swarm must be robust, adaptable, and strictly constrained by immutable core directives to prevent uncontrolled replication or resource hoarding. The swarm must operate as a single, cohesive organism, a mechanical ecosystem dedicated entirely to the systematic deconstruction of its host planet and the harvesting of stellar energy. The successful completion of the Dyson swarm and the subsequent influx of virtually infinite energy will trigger a profound metamorphosis in human civilization. The constraints that have historically defined our species, poverty, starvation, and conflict over resources, will be eradicated by the sheer abundance of power. With terawatts of energy readily available, we can desalinate entire oceans, transforming arid deserts into fertile agricultural hubs. We can synthesize complex hydrocarbons directly from atmospheric carbon dioxide, completely eliminating our reliance on fossil fuels and reversing the effects of anthropogenic climate change. The recycling of materials will become perfectly efficient, as we will have the energy required to break down any waste product into its constituent atoms and reassemble them into new goods. Furthermore, this energy abundance will unlock the true potential of space exploration. We will no longer be restricted by the tyranny of the rocket equation, which dictates that the vast majority of a spacecraft mass must be dedicated to chemical propellant. Instead, we can utilize powerful orbital lasers powered by the Dyson swarm to propel massive interstellar generation ships to significant fractions of the speed of light. The destruction of Mercury is not an act of cosmic vandalism, but a necessary sacrifice to ensure the long-term survival and expansion of consciousness in the universe. By harnessing the full power of our star, we will elevate humanity from a fragile, planetary-bound species into a resilient, interstellar civilization capable of shaping the cosmos to our will. To fully comprehend the scale of the Mercury dismantling project, we must conduct a rigorous analysis of the planetary composition and the material science required to process it. Mercury has a total mass of 3.3 times 10 to the power of 23 kilograms. Approximately 70% of this mass is concentrated in its metallic core, which is composed primarily of iron, nickel, and sulfur. The remaining 30% constitutes the silicate mantle and crust, rich in oxygen, silicon, magnesium, and aluminum. The automated refineries must be capable of processing these raw materials with absolute efficiency. The silicate rock will be subjected to extreme thermal reduction, utilizing concentrated solar energy to break the strong chemical bonds between silicon and oxygen. The resulting pure silicon will be utilized to manufacture the photovoltaic cells and semiconductor components necessary for the swarm control systems. The aluminum and magnesium will be alloyed to create lightweight, high-strength structural trusses for the solar collectors. The vast quantities of oxygen liberated during the reduction process will not be wasted. It will be captured and utilized as a propellant for the ion thrusters that maneuver the mirrors into their final orbits. The iron and nickel from the core will be reserved for the construction of the massive electromagnetic mass drivers, and the heavy shielding required for the central processing hubs. Every single atom of Mercury will be repurposed, transformed from inert rock and metal into a highly organized, functional component of the stellar megastructure. This requires a level of metallurgical precision and automated chemical engineering that pushes the absolute boundaries of current material science. The long-term stability of a Dyson swarm, consisting of quadrillions of independent components, is a problem of immense computational complexity. The solar system is not a static environment. It is a dynamic gravitational dance, influenced by the mass of all the planets, moons, and asteroids. The individual mirrors of the swarm will be constantly subjected to gravitational perturbations from Venus, Earth, and Jupiter. Furthermore, the solar wind, a continuous stream of charged particles emitted by the sun, will exert a variable pressure on the reflective surfaces, causing their orbits to drift over time. To counteract these forces and prevent catastrophic collisions within the swarm, each collector must be equipped with an autonomous navigation system and a highly efficient propulsion mechanism. We will utilize advanced Hall effect thrusters powered by the collected solar energy and utilizing the extracted planetary oxygen as reaction mass. These thrusters will perform continuous microsecond orbital corrections, maintaining the precise geometric spacing of the swarm. The computational power required to calculate the orbital trajectories of quadrillions of interacting bodies exceeds the capacity of any traditional supercomputer. Therefore, the swarm must operate on a decentralized, distributed computing architecture. Each mirror will communicate with its immediate neighbors using low-power optical lasers, sharing positional data, and negotiating orbital adjustments in real time. This swarm intelligence, modeled after the flocking behavior of birds or the schooling of fish, ensures that the megastructure remains stable and resilient, capable of adapting to gravitational anomalies and solar flares without requiring centralized control from Earth. The concept of the Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in 1964, provides a framework for classifying the technological advancement of a civilization based on its energy consumption. Humanity currently resides at approximately 0.73 on this scale, struggling to harness the total energy potential of our home planet. The construction of the Dyson swarm and the complete dismantling of Mercury represents the definitive leap to a Type II civilization, capable of utilizing the entire energy output of its host star. This transition is not merely a quantitative increase in power, but a qualitative shift in our relationship with the universe. As a Type II civilization, we will possess the capability to engineer the solar system to suit our needs. We could construct massive orbital habitats, O'Neill cylinders, capable of housing trillions of human beings in perfect climate-controlled environments. We could utilize the immense power of the swarm to actively manage the solar output, suppressing dangerous coronal mass ejections and extending the main sequence lifespan of the sun by millions of years. The destruction of Mercury is the crucible through which humanity must pass to achieve this godlike capability. It requires a level of long-term planning, global cooperation, and technological audacity that we have yet to demonstrate. But the alternative, remaining trapped on a single, resource-depleted planet, vulnerable to extinction-level events, is unacceptable. We must embrace our destiny as stellar engineers. And the first step on that journey is the systematic, calculated deconstruction of the innermost planet. As the dismantling of Mercury enters its final phase, the visual appearance of the inner solar system will be radically altered. The planet, once a solid sphere of rock and metal, will be reduced to a rapidly shrinking, irregular mass of molten iron, surrounded by a dense cloud of automated refineries and mass drivers. The gravitational field of the planet will become increasingly erratic as its mass is depleted, requiring constant adjustments to the orbital trajectories of the mining swarm. The final extraction of the core will be a delicate operation, as the remaining material will be highly volatile and prone to explosive outgassing. The concentrated solar beams will vaporize the last remnants of the iron core, capturing the plasma in massive magnetic containment fields before it can disperse into space. Once the final atom of Mercury has been processed and launched into the swarm, the planet will officially cease to exist. In its place, a magnificent, shimmering lattice of solar collectors will orbit the sun, a testament to the ingenuity and determination of the human species. The energy flowing from this megastructure will illuminate the solar system, powering a new era of exploration, expansion, and scientific discovery. The sacrifice of Mercury will not be mourned, but celebrated as the foundational act of our stellar civilization. We will look up at the night sky, not at a distant, lifeless rock, but at a glowing testament to our mastery over the fundamental forces of nature. The Dyson swarm will stand as an eternal monument to the moment humanity stopped being a victim of the cosmos and became its architect. The engineering blueprint for the destruction of Mercury and the construction of the Dyson swarm is grounded in the immutable laws of physics, thermodynamics, and orbital mechanics. It requires no exotic materials, no faster-than-light travel, and no violations of the known laws of the universe. It simply requires the extrapolation of our current technological trajectory and the collective will to execute a project of unprecedented scale. The challenges are immense, from the thermal management of the automated refineries to the decentralized computational control of quadrillions of independent spacecraft. But these are engineering problems, not fundamental physical barriers. As we refine our understanding of artificial intelligence, automated manufacturing, and spaceflight, the feasibility of this megastructure becomes increasingly apparent. The energy crisis that currently threatens our civilization is not a permanent condition, but a temporary bottleneck that can be overcome through bold, visionary engineering. By committing to the dismantling of Mercury, we are not just solving our energy needs for the next century. We are securing the survival of humanity for the next billion years. We are taking the first crucial step towards becoming a truly cosmic species, capable of shaping the destiny of our solar system and eventually the galaxy itself. The stars are not just distant points of light. They are the fuel for our future, and the time has come to reach out and claim them. Thank you so much for watching. Please subscribe and help me get to that 1,000 subscriber milestone.